Hello, AP Chemistry students. We're now at section 1.6 on photoelectron spectroscopy, which is an analytical technique used to gain insight on the electronic structure of an atom. So our learning objectives for this one are to explain the relationship between the photoelectron spectrum of an atom or ion and A, the electron configuration of the species, and B, the interactions between the electrons and the nucleus. So this is going to dip into a lot of the ideas that we covered in section 1.5, mainly about Coulomb's law and how the force between two charged particles are going to be affected by the charges of the particles themselves and the distance between them. And then also, we're going to be talking about the Schrodinger model of the atom and how those electrons are organized into energy levels, subshells, and orbitals in somewhat of a complex pattern. But we'll also find that the photoelectron spectroscopy gives us sort of real life data that proves the Schrodinger model. So how it works is it's not all open like this, but this is like a summary of all the parts within the instrument. So we start with a photon source. So our photon source is basically a high energy laser beam. Photons are just another word for particles of light, which are just little packets of energy. And this is really high energy light. This is like ultraviolet or X-ray light. So we have this high energy beam of light that is hitting the sample, and the sample is going to be absorbing that energy. And that's going to excite the electrons. And what I mean by excite the electrons is that the electrons themselves are going to absorb that energy. And that energy is going to be enough to overcome the force of attraction of those electrons from the nucleus. And based off of where those electrons are in the structure of the atom, if they're like inner shell electrons or outer shell electrons, they're going to leave the atom, they're going to be ejected, and they're going to have a certain amount of energy that is correlated to how much energy it took to pull those electrons off in the first place. And those electrons are going to go into this chamber here, and then they're going to go to a detector or an energy analyzer that's going to read how much kinetic energy they have. And the kinetic energy that they have when they hit the detector is going to be directly correlated to how much energy it took to remove them from the atom in the first place. And we know that based off of this equation here. So here we have the energy of the incoming light from the laser source, and that's going to be equal to the ionization energy of the electrons and the kinetic energy that they have afterwards. If you think about it, we have a constant source of the same amount of energy. It's hitting the sample. Some of that energy is being used to pull the electrons off of the atom. And then based off of how much energy was used in that first step, they're going to have a certain amount of kinetic energy left over. So say we have a inner shell electron that's tightly bound to the nucleus. That's going to take a lot of energy to remove, which means that a lot of the energy is going to get used up, and there's not going to be enough kinetic energy or not much kinetic energy left afterwards. Whereas an electron in an outer shell, it's going to be a lot less energy to remove, which means it's probably going to have a much higher kinetic energy when it comes off. So a good analogy for this is to imagine that there's a table, and then I take a very heavy book and put that on the table, and then also a very light pen and put that on the table. And then I walk up to the table and I lift my hand up high, and then I reach down and swat the book. And this will be enough energy to knock the book off the table. And it's gonna get lifted up off the ground or lifted off the table, and it's gonna fly a couple feet, and then it's gonna land on the ground. And when I do that again, when I walk back to the table, put my hand up in the air, and then swat again at the pen, assuming with equal amount of energy, we'll see that the pen goes basically flying across the room. And we know that the pen and the book were both held to the table with gravity. So there was a force holding them there, much like the force holding the electrons to the atom. And then an outside source of energy comes in and swats them, much like the energy from the laser in the photoelectron instrument. And then when the book and the pen leave the table after being swatted, they have a certain amount of energy in the form of kinetic energy that will sort of determine how far they fly after they're knocked off. And if you think about it, if I'm supplying an equal amount of energy to both of the swats, the amount of force that's holding them there is going to dictate how much energy they have when they leave. because it took a lot of energy to get the book off the table, so it only had so much kinetic energy after, and it was only able to fly so far. Whereas the pen was not held very tightly to the table because it didn't have enough mass to be attracted to the table with as much force as the book. So when I swat that one, there's a ton of energy left over because it didn't take that much energy to get it off the table in the first place. That's why I was able to fly across the room afterwards. So what a photoelectron spectrum actually looks like is a graph like the one below here. So on the x-axis, we're going to be reading the ionization energy of the electrons, which is calculated through that equation I showed you. The detector reads the kinetic energy, and then it subtracts that from the energy of the incoming light to solve for the ionization energy of the particles themselves. And then on the y-axis, we have the relative number of electrons. And this is pretty similar to the relative intensity that we saw on the mass spectrum graphs. They basically show us how many times things are hitting the detector corresponding to that value. So if we look at this graph, we can kind of read what it's telling us and gain some insight from it. So let's start from the left. So first off, you'll notice that it starts around 84 and then goes to 2. So the x-axis is technically backwards. There's a good reason for doing that. That is related to the electron configuration, but we'll kind of get into that in a sec. So let's analyze this first peak. So in this first peak here at 84, we can see that based off the y-axis, there's a certain number of particles that are hitting the detector that correspond to ionization energies of 84 megajoules per mole. The x-axis is always going to have some amount of energy per mole as its unit. So we have a certain amount of energy that corresponds to this ionization energy, or a certain amount of electrons that correspond to this ionization energy. And then as we go along the x-axis, we actually see a lot of nothing. So you see these two dashed lines here. That actually represents a skip in the x-axis. There's just no data there. So instead of having this really long graph where nothing's happening, we basically just deleted a big portion of it. And the next time we see any data is here, and this is going to be around like 4.5 to 5. It's kind of hard to tell from this axis, but here we see another peak, which is pretty much the same size as the first peak. So whatever these two peaks represent, they are representing the same number of electrons hitting the detector, just at different energies. This one corresponding to an ionization energy of 84, and this one corresponding to an ionization energy of 4.5. And if we look at this last peak here, which is at an even lower energy, around like probably 2.2 or something like that, we see that this peak is a lot taller. And if we compare the relative sizes of these two peaks, we could say that this peak is about maybe 3 times bigger than this peak. So what this graph is telling us is that whatever element that we're studying here is producing 3 different peaks. So that means there's electrons in this atom that correspond to 3 unique locations that have 3 unique ionization energies associated with them. And we also know, based off the fact that there is a huge gap in between here, that can be explained by Coulomb's law. Because if you think about inner shell electrons versus outer shell electrons, the amount of energy it takes to remove them is exponential based off the distance. The farther away you get from the nucleus, the easier it is to remove. So we can assume that this peak here corresponds to inner shell electrons, and these peaks over here correspond to outer shell electrons. And we'll also notice that this inner shell only has 1 peak, but this outer shell has 2 peaks. And that also correlates to the Schrödinger model, the way we talked about it last time in terms of the subshells that are available at different energy levels. So we can assume that this first peak here is associated with the 1s subshell, or the 1s orbital of the atom, the orbital that is closest to the nucleus and therefore requires the most energy to take electrons from. And then if we look here, we have another peak that's the same size. And we can assume that this is also going to be an S subshell, but this is going to be our 2s subshell. And we also know that S subshells, assuming that they're full, can hold a maximum of 2 electrons. So we can kind of assume that both of these peaks are going to be associated with a y-axis value of basically 2 electrons. So if we compare that peak now to this last peak here, the one we said that was about 3 times bigger, we can assume that since this is representing 2 electrons, that this is going to be representing 6 electrons. and we know that P subshells are able to hold 6. So we can assume that this is the 2p peak of the atom. So from this, we can basically read the electron configuration. We know that the electron configuration of whatever this element is going to be 1s2, 2s2, 2p6. And if we consult the periodic table, we can see that that is neon. So we here have a photoelectron spectrum of the element neon. So what element is this? So we can kind of give this a similar analysis. We can try to figure out how this pattern of peaks maps to an electron configuration and what that says about the construction of the atom and where all of the electrons are. So we have a similar situation here where we have a peak out at a really high energy, and then we have a certain amount of x-axis that is being skipped, and then another peak of the same height. So we can already tell that we have 1s2, 2s2, and then this also looks like our 2p6, like the last one, except now we have another grouping of peaks over here. So we can assume that this is our first energy level, this is our second energy level, both of those are full. Whatever element this is has electrons all the way out to the third energy level. But you can see here that we have another peak that is the same size as these ones, so we can assume that's another S peak. So we have 1s2, 2s2, 2p6, and then 3s2. But this last peak here isn't totally full because it's not as high as this peak here. We would assume that 3p6 would be the next part of our configuration, assuming that all the subshells were full. But since this is not as tall as the other p peak, we can assume that the p subshell of this element is not full. So let's look at this peak and try to figure out what our relative number of electrons that are going to be associated with this peak are. Well, we know that these 3 peaks here, being S subshell peaks, contain a maximum of 2 electrons. And then this is going to be 6, which is 3 times taller than that. We can see that this peak here, this last one, is only a sliver taller than the one before it. And if this is 2, and we cut that in half, we can think about how tall each peak would be based off 1 electron. So we can see that here, that this is probably going to correspond to 3 electrons. One, because it's like basically 1/3 taller than this one. And also because it's 1/2 of our 2p6 peak's size. So we know that this is going to be the 3p peak, but it's not going to be 3p6, it's going to be 3p3. So now our electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. And what element does that correspond to? Well, that is phosphorus. So another important aspect of photoelectron spectroscopy is understanding how the ionization energies on the x-axis are due to the interactions between electrons and protons in the nucleus, and how that is going to differ between different elements. You probably saw that in the 2 different ones that we've seen so far, that 1s peak was at different energies. In the first one we saw of the neon spectrum, it was around 84, but then the one in the phosphorus spectrum was around like 100 and something. So that 1s peak occurs at different energy for different elements. And that's largely due to the fact that different elements are going to have a different number of protons. So therefore, the attractive force of the nucleus is going to differ from element to element. So say we were to plot 2 elements using PES on the same graph. And what we're going to see is based off of how many protons that element has, it's going to shift the spectrum in one direction or the other. So on this graph here, we have an overlay of the spectrum for sodium and the spectrum for potassium. Sodium and potassium are both in the same column on the periodic table. They both have the same number of valence electrons, except for potassium, since it's in the 4th row, it's going to have a 4th shell, whereas sodium is going to have 3. So let's look at our graph here. So the blue lines represent the sodium, and the pink lines represent the potassium. So let's look at the sodium spectrum first. So we have 1s2, 2s2, 2p6, and then 3s1, since we have 1 valence electron in our last shell. And then if you look at the potassium spectrum, you can see that it's shifted to the left on the x-axis. The 1s peak is at a higher energy than the 1s peak for sodium. And that's due to what I was just explaining earlier, where potassium being further down in the periodic table, having a bigger mass, having more protons, is just going to have a stronger pull to its nucleus. So our 1s peak is going to be at a higher energy. So we have 1s2, 2s2, 2p6, and then we have 3s2 and 3p6, since that third subshell is full, or that third energy level is full. And then we have our 4s2 peak. And you'll notice here that our last electron, our last valence electron for potassium is actually at a lower energy than the one for the 3s. And that makes sense based off of stuff that we've said before about ionization energy. The farther out the electron is from the nucleus, the easier it's going to be to remove. And that's why the furthest electron in potassium is going to be easier to remove, but the one closer to the nucleus is going to be harder to remove. So you can see that the overall spectrum of potassium is a lot wider in terms of its variance of energy than one for potassium. So if you're ever having to plot two PES on the same graph, remember to think about how many protons that thing has and how that's going to shift it on the x-axis. More protons means it's going to be shifted more towards higher energy. But the more peaks it has, the more those valence shell electrons are going to be further out in the low energy side of the spectrum. So I want y'all to try to practice drawing these. I don't care too much about the actual energy values as long as you're getting the relativity between spectrums right. But I want you to try to practice drawing a spectrum of magnesium and aluminum overlaid on the same graph. So magnesium and aluminum are kind of close to each other on the periodic table, but they're going to differ by the number of electrons and the occupied subshells. So pause this video real quick and try to draw a photoelectron spectrum containing both magnesium and aluminum overlaid. So make sure to label your x-axis as ionization energy and your y-axis as relative number of electrons. Okay, so let's look at the answer here. So we're going to see a pretty similar thing here to the spectrum of sodium and potassium that we looked at earlier. Sorry, my picture is kind of hard to read here, but the black line is representing magnesium, and this is more of a blue line for aluminum. So let's look at the magnesium. So we have 1s2, 2s2, 2p6, and then 3s2. So that's corresponding to the full spectrum of magnesium. And then let's look at aluminum, which is slightly heavier. It has more protons and therefore a stronger attraction for its nucleus to all of the electrons. So that's why the blue peak here is shifted slightly to the left of the 1s peak for magnesium. So we have our 1s2, our 2s2, and our 2p6, and then our 3s2. And then since aluminum has one more electron than magnesium, we know based off of the order of the subshells that that electron is now going to be in the 3p subshell, but we only have one more electron, so we only need a little tiny peak here at the end. And from this, we can see that the first ionization energy of aluminum is lower than the first ionization energy of magnesium. However, on average, the electrons from aluminum are harder to remove due to that stronger force from the nucleus. And that is all for section 1.6. So I'll see you in the next one.